What do you get when you combine gravity, nuclear physics, and the most massive star in the universe? If you said something like a black hole, you'd be kind of right, but not quite. You'd actually be describing an object known as a neutron star, which is basically a dead star that has been squeezed into an extremely dense ball by gravity. And because these things are so darned dense, they can spin thousands of times per second without falling apart. They are the fastest spinning objects in the known universe and are called relativistic rotators, and as wild as it is to imagine something spinning at thousands of rotations per second, scientists think that some neutron stars could be spinning even faster than that, but how fast is too fast for a neutron star? Can these objects spin so quickly that they literally rip themselves apart? That's what we're talking about today on SCI Show Space. Neutron stars form when a massive star goes supernova, which is the big explosion that marks the end of a star's life. Basically, the star has used up all of its nuclear fuel, so it doesn't have any more energy to fight against the crushing force of its own gravity. And as the star collapses in on itself, everything gets really squished. All of the matter in the star is forced together so tightly that protons and electrons are smashed into each other to form neutrons. And that's why it's called a neutron star. It's mostly made out of neutrons. Now, before the neutron star gets to this super-dense stage, it is rotating, probably because it was a rotating star at one point, and in general, things tend to keep rotating unless something external comes in and changes their angular momentum. So the neutron star inherits its rotation from the star it replaced. But because the structure of the star has changed so dramatically, everything is way more compact. Most of the mass of the original star was in the outer layers where the energy was generated, but those outer layers were also spread out over a very large radius. The neutron star has the same amount of mass but much smaller radius. So all that mass is concentrated near the center. And since angular momentum depends on mass distribution, the distribution of mass around a neutron star is going to be different than it was around the star it replaced. We don't know exactly how the collapse happens or how the neutron star will distribute its mass, but if we assume that the core keeps its original rotational speed, and the outer layers do not contribute to the rotation of the neutron star, then we can calculate the upper limit for how fast a neutron star can rotate based on how fast the star was rotating just before it became a neutron star. Using this method, scientists think that a neutron star can keep its maximum speed from when it was a star, which means that some neutron stars may be rotating up to 716 times per minute. That would be about 12 rotations per second, but we know that not all neutron stars rotate this quickly. In fact, most of them rotate slower than once per second. So where did this extra energy go? One possibility is that the neutron star is transferring angular momentum to a companion star through gravitational waves, and while that seems possible, it would require a very specific setup. Another possibility is that as the star becomes a neutron star, some of the energy in its rotation is radiated away as light. This process is called gravitational radiation, and it's basically what we expect should happen with any accelerated mass in this scenario. The star is rotating faster than it can radiate energy away, so it begins to slow down until it reaches a steady state where the two balance each other out. This process would depend on the exact mechanism by which a star becomes a neutron star. Since we don't fully understand that process, we can't say for sure how much energy is released during the transition and therefore how much the neutron star slows down. But astronomers can observe the rate at which neutron stars are spinning and use that to work backwards and infer how fast they might have been spinning originally. By looking at the slowing rates of isolated neutron stars, scientists estimate that if they were initially rotating at the maximum speed, they would have radiated away 10% of their total energy during the conversion from star to neutron star. Other studies suggest that the energy loss could be as high as 30. To lose that much energy while becoming a neutron star, the star would have had to be rotating very quickly. We're talking up to 13,000 kilometers per hour at the equator. At that speed, airspeed would reach 99% the speed of light. Unfortunately, there are conflicting results and lots of uncertainties. So for now, scientists aren't sure exactly how much energy neutron stars radiate away as they become neutron stars. There is also the possibility that the neutron star is sharing angular momentum with whatever it is interacting with, whether that's a companion star or not. For example, a neutron star can interact with a cloud of gas or plasma and transfer some of its angular momentum to it. The problem with this is that it is really hard to observe interactions between neutron stars and the stuff around them because most of that stuff is invisible. Gas clouds are difficult to spot because they emit very little light unless something exciting is happening, and if the neutron star is in a binary system with another collapsed star, like a white dwarf or another neutron star, then it'll be hard to tell if either of them are spinning. It's only when these systems are in an active phase, meaning the two objects are exchanging material, that they become bright enough to see, and when scientists do observe these active systems, they usually don't catch them at the peak of their brightness, so it's hard to draw conclusions about how fast the neutron star was spinning originally. But here's the good news. One day, scientists might be able to answer all of these questions. That's because they can recreate the conditions under which stars collapse in labs on Earth. Experiments like the Joint European Torus Project are recreating conditions inside stars to study what happens when they collapse and how elements heavier than iron are formed. Meanwhile, experiments like the National Ignition Facility at the Lawrence Livermore National Laboratory are focusing on fusion reactions that occur in stars. By better understanding how stars work, scientists can improve their models of stellar evolution, which can help them better predict what will happen to a star when it runs out of nuclear fuel and what happens next. So maybe one day soon we'll know how fast the fastest spinning neutron star can spin, although if we find an even bigger star and watch it explode, we might find an even faster neutron star. It's an exciting time to be learning about the universe. And if you want to be a part of it, you can start by supporting us. Your support helps us make videos like this and allows us to keep making them free for everyone forever. We've got some cool perks for our supporters, like blooper reels and behind-the-scenes posts, so check it out, and thank you for watching.